So, hello everybody. Hello, hold on. Hello, everyone. How are you? Fine, thank you. Oh my God. Anyway, uh, welcome to another video of mine. As you can tell by last video, uh, now it's the turn again for Michael Artin's algebra book. We're going to run through some other problems for about an hour, 50 minutes or so, and then we'll call it a day. I'll put my microphone right here, and then we'll call it a day. All right. If you can see my screen. All right. So last chapter we left it. We finished last chapter. We finished the following problem and said get the general the general formula for this matrix. But now what we're gonna do is do an extended version, and by extension, a slightly more complex version. We're doing a 3 by 3 of the same what's that format, right? So, um, obviously for n equals 1, it's the same. It's the same. What we're gonna do is run through some examples up until um, we feel like we can find a pattern, and then that's where we get our formula or our general form. Uh, but yeah, for n equals 0, it's gonna be the I, you know, the identity matrix. For n equals 1 is that. For n equals 2, for n equals 2, um, it is this times itself. Right? Hold on. Ah, dang it. Dang it. Duplicate. There we go. Times itself. Hold on. And then duplicate times itself is, I don't know. This is a 3 by 3, luckily, so my calculator can do that. Um, Matrix, where's matrix? Matrix. All right, we have a 3 by 3 of 1, 1, 1, 0, 0, 1, 1, 0, 0, 1. And so, boom, boom, we get 1, 2, 3, 1, 2, 1. Okay, 1, 2, 3, 0, 1, 2, 0, 0, 1. This is for n equals 2. Right, right, right. For n equals 3, it is the same matrix. Duplicate. It is the same matrix and multiplied by the original matrix. That's a process. That's how you do exponents, if you didn't know. So yeah, so we take this matrix up, that 1, 2, 3, 0, 1, 2, 0, 0, 1. And we get the other matrix. You say 3 by 3, 1, 1, 1, 0, 0, 1, 0, 0, 1. No, wait. Ah, dang it. 1. There we go. 1, 1, 1, 0, 1, 1, 0, 0, 1. There we go. And we do A times B. And we get 1, 3, 6, 6, 0, 1, 3, 0, 0, 1. From here you might be able to pick out some of the format of the final general form of the matrix. If n equals 3, just to see it better, right? But I'm gonna do about I don't know, one or two more, just to be sure. You can never have too many cases. So this is like a crime scene. You know, the more evidence, the better, right? Don't be ashamed. Look, don't be ashamed if you have to do more. God damn it! Don't be ashamed. There we go. If you have to do more edge cases or things to see it clearly, because at the end of the day, you're still gonna arrive at the same answer. So we have 1, 3, 6, 0, 1, 3, 0, 0, 1. And our second matrix is still the same. Yep. So we do A times B. And we get 1, 4, 4, 10. Wait, 1, 4, 10, 0, 1, 4, 0, 0, 1. That's for n equals 4. And for our last one, hopefully I can derive it from 5 test cases, or else might look like a little bit of a fool. Nah, I don't give a fuck. N equals 5, right? All right, pull it down. Duplicate. Right, boom. Now we go 1, 4, 10, 0, 1, 4, 0, 0, 1. And we'll do A times B. 1, 5, 15. 0, 1, 5, 0, 0, 1. Down. All right, n equals 5. So we have these 5. Well, actually, let me put this. Oh, where you go? There we go. Dang. We have these 5. So we have these 5 matrices representing 5 powers of the same matrix. There's 1, 2, 3, 4, 5. So you can quickly see that there's some sort of a since this is an upper diagonal, or in general diagonal matrix, um, the diagonals and the zeros are not going to change with multiplication, and so we can do this. All right, as n approaches infinity, right? So we go 1, 0, 0, 0, 0, 1. Right here, 1. That's what we first see. Well, that's what we first notice when we start working through the cases, right? So next thing we notice, we can go from like outside in this case, peel it like an onion, as you may. That what does change is the three upper right elements of each matrix, especially these two are the same in every single one matrix, right? And another thing is that on each iteration or each power, these are the same as the power of the matrix. So we can say that n goes in here. Now for the more complicated part, more involved part, is the upper right corner of the matrices, right? We can put them on a list. We have them 1, 3, 6, what's that? 10, 15, right? 10 and 15. All right. So we can try to we can try to derive like a sort of pattern from here. If we look at the addition, right? In this case, you add 2, and you add 3, then you add 4, then you add 5, right? There is some sort of, yeah. However, you cannot, like the way it's formatted, you cannot put a sum, right? You cannot put a summation to like I equals 1 to infinity. It's like I, right? Yeah. You can't do that, right? Or I to n. It is not advisable. So the way the book puts it is, or like the way I've looked at it, the way I found out through the internet and asking around, it is. Wait, I forgot. Hold on. I forgot. Honest, I completely forgot. So just gonna do fuck um that there. Um, Now that we got that, I am gonna try some, because I remember it was some like n or two or 2 times n plus 1. It was 2 times n plus 1 divided by n. So like if we have 1, it would be, oh, that's not it. That's not it. No, it was 1 plus 1. No. No, 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 no. Yeah, I don't remember. I don't recall. So that's basically, yeah. So like when n equals 2, you have to add 2. You have to add 1, and then plus 2 is 3. If n equals 3, you go 1 plus 2 plus 3, right? Yeah. In which case it would be, no, yeah, that's good. It's 1 is good. 1 is good. 1 plus 2 plus 3. Yeah. So yeah, that's my answer. I know this is not quite the rightest answer there is, but that's my answer. Probably not the rightest. Let me check. Let me check. Let's do another test case we have. Hold on. I said I didn't want to make a fool out of myself, but I am currently making a fool out of myself. Second matrix is still the same. Yep. So we do A times B. Yep. The other number is 21, which is plus 6. So I guess that's, yeah, I guess that's right. But it's not. It's not the form. It's not in the format I saw it on the internet. Um, but yeah, it's an answer. It is an answer. So yeah, there you go. That's it. That's it for that question. It was a long one. That was quite a long one, gotta say. All right, so next question. Ah, okay, it's a 3 by 3. Okay, I'm gonna do. Okay, so I'm gonna say the question and then I'm gonna try to explain some things. So I have 1, 0, 1, 2, 0, 1, 0, 3, 0, 1 times 1, 2, 3, 4, 2, 3, 5, 0, 4. All right. Here we go, and it goes like this and like this. If you know about this, you already know what I'm doing. Uh, for those of you who do not, I don't know, 90% of my audience, probably, maybe, I don't know, might always be wrong. Um, what I'm gonna do is called block multiplication. It's like um, if you separate your whole matrix into uh little chunks within, it's gonna be a matrix of matrices. You get a block matrix, and if you multiply two block matrices, you are doing block multiplication. The way you do it is basically the same as normal matrix multiplication when it comes to the actual individual entries, but it's the size of the blocks that change, and that's what makes it different. So you can have different matrices within one single matrix. Um, I've looked it up a little bit because I'm obviously like, what the hell is this for? You can do the same with multiple matrices, um, but apparently it's very useful in things like physics and to make matrix multiplication faster in computers. Um, which not sure. But anyway, this is the next question. There's another that's a 4 by 4. I'm not gonna put myself through that. Mm-mm. Uh-uh. So what I'm gonna do is I'm gonna use my handy dandy calculator. I'm gonna do 0, 1, 2, 0, 1. Ah, no, no, hold on. Yeah, right. 0, 1, 2, 0, 1, 0, 3, 0, 1. And we got 1, 2, 3, 4, 2, 3, 5, 0, 4. Um, yep, that's good. Then we do A times B, and our resultant matrix is 14, 14, 2, 11, 4, 2, 3, 8. I think that's an 8. 6, 13. Okay. Okay, so now that we got the entries, right? We need to define the box sizes. Luckily, in this case, it's gonna be pretty much the same. So, yeah, I don't really understand it all that much, you know. Not yet. I would need some more practice and some more investigating on the matter and see how it is applied. But yeah, that's how that's how you do it. If the boxes are the same size for both matrices, then the resulting product is gonna have the same size boxes. Um, generally, there were other cases in the book where the boxes had different sizes. Um, let me let me. Where is it? I think I skipped it. Yeah, I think I skipped it. Anyway, that's it for that question. That's the answer. Yeah. Anyway, 120. 120. What was 120? Hold on. One, one. Where is it? Ah, it's all the way over here. 120, 120, 120. I went too far back. Damn. I want to see if I want to do this question in this video. Uh, oh, this is block multiplication. Numbers, let me see. Okay, yeah. I'm not gonna do that. I'm gonna skip that question because I really don't want to do it. I don't really like block multiplication as of now. So, question 10. Question 10. AB. Let's A, B, symbol, symbol, and by n, right? They're square matrices, right? So one is, the first part of question 10 is like, when is A plus B times A minus B equals A squared minus B squared? All right, so we're basically asking, when does the usual difference of squares property of numbers apply with matrices? And if you've taken linear algebra before or know about linear algebra, remember about what was that? Eigenvectors and eigenvalues and matrices and all that. The way you this is before, like, this is uh, my reasoning before starting to work on it. Um, you would have to treat these matrices as numbers, and the way you represent numbers as matrices is through only having numbers in the diagonal, right? So if you have, so for example, let's say, let's go by eigenvectors. So like, to use this eigenvalue, um, to multiply it or use it for other multiply or subtract with other matrices, you'd have to multiply it by I. In other words, you have to multiply it by the um, the identity matrix, right? So that all of the non-zero entries are like that. So yeah, that's generally the way it would have to be a diagonal matrix. So let's try to work it. Let's try to show it. That is my thought process. So I'm gonna try to show it with this question. Right? So let's say A. Since this didn't specify anything, I'm gonna go with like a. Let's do a 2 by 2, right? Because it's gonna be, if it's true, it's gonna be the same for any and all, right? I just want to show it quickly and without too much trouble, right? I don't want to get into a lot of computations and stuff. Ew. So let's say A equals A, B, C, D, right? Where A, B, C, D are real numbers, symbol. Wait, I didn't do it right. The R is always like kind of hard to get it right. There we go. Ah, good enough. Simple. Anyway, B is X, Y, Z, W. Uh-huh. Where, you guessed it, X, Y, Z, W are real numbers. Simple. God damn it. Real numbers. There we go. Nah, it's not right. Still. Oh my god. Ah, hold on. This is very important to the proof. Oh, that is so beautiful. Oh, that is a good R. That is a very good R. I like drawing symbols. I don't know why. So, uh, therefore, A plus, dang it, A plus B equals, right? A plus B equals A plus X, uh, B plus Y, C plus Z, and D plus W, right? Right? Ah, dang it, right? And A minus B, dang it, minus B is, you guessed it, just gonna copy it. I'm just gonna copy it. You guessed it. It's the same but minus, right? Minus, 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 minus. A squared, not cubed. Hold on. A squared is I'm gonna have it there so I can visually see it. My little smooth monkey brain is too small and smooth to do it on my mind, so I'm gonna have it right on my face. That sounded so bad. Pause. Continue. Now it's gonna be a squared, uh, a squared plus bc. Mm, it's gonna be ab plus bd. This is gonna be ca. Yeah, ca plus dc. And it's gonna be cb plus d squared. You can kind of see where I'm going now. If you maybe not. I'm not sure. Okay. Let's keep going. B squared. Again, I'm gonna have it in front of me because my little monkey brain is too smooth and monkey-like. Alright, duplicate. There we go. So this is x squared plus yz, right? And then xy plus yw, and then zx plus wz, and then zy plus w squared. Right, 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 right. Um, so, and so a squared plus b squared equals this thing. Actually, it would be minus. Duplicate. Actually, it would be minus a squared. The question says minus, right? Yeah, a squared minus b squared. Minus b squared. Yeah, a squared minus b squared. B squared, duplicate. Boom. It will be this, which this is why I said I wanted to do it on a 2 by 2 because it was gonna be a really um is this listening to me? Are you listening? Hopefully you're listening to me because I'm gonna be crying. Like the little microphone icon is not showing up. Um but if you're listening to me, great. Anyway, hopefully you're listening to me. Now, um so we got this thing times this thing. Oh boy. We got a squared plus bc times x squared plus yz equals, this is a squared x squared uh, plus a squared yz plus x squared, dang it, x squared bc plus yz bc, right? And that's gonna be added. Let's have it. 32 minutes. Wow, that's quick. That's gonna be added to uh, right, ab plus bd times zx plus wz. So we get ab zx plus abwz plus, hold on, plus bdzx plus bdwz. And it's this whole thing. This whole thing. Oh my goodness. No, wait, we are actually. I'm so dumb. We're not multiplying. I forgot. My B. My B, I forgot. We are subtracting, not multiplying. Imagine there's a subtraction symbol here. Oh goodness. So this is gonna be a squared minus x squared plus bc minus yz plus bc minus yz. Right, and the next one is gonna be ab minus xy plus bd minus yw, right? We got ca minus zx plus dc minus wz, and then we got cb minus zy plus d squared minus w squared minus w squared. Right? Okay, so this is what we got. So the rule says, or the question says, that a plus, hold on, a plus b times a, and dang it, a minus b should equal, or when does it equal a squared minus b squared? Wait, did I do the multiplication of a plus b and a minus b? I did not. Okay. Okay. Um, a plus b. This is so long. A minus b. I don't like this. I want to go home. Mom. Anyway, boom. Duplicate. Where is it? Over here. There we go. And a minus b. It's right here. Duplicate. Where is it? Over here. Right. So, my goodness. So we got, oh, this is basically, oh, this is a difference of two squares. This is a difference of two squares, so it's a squared minus x squared. This is z squared minus z squared. B squared minus y squared. And d squared minus, we're having some technical difficulties. Hold on. Okay, we had some technical difficulties. So yeah, what I was saying, d squared minus w squared. That is the resulting matrix. So we went from here down to here, and this is what we got. And so when are these two matrices equal, right? You can tell that we got a squared minus x squared here, uh, d squared minus w squared here, right? They're the same. Everything else, um, it can be whatever. It has to be zero. Sorry, I got a little lost in thought here. The technical difficulties are rough when you're already kind of maybe in the zone. Um, so yeah, uh, this is what I got from the left side. This is what I got from the right side. So the only, oh my goodness, what is it? Hopefully it goes right, or else the video is gonna stop abruptly here because I am a little fed up with these technical difficulties. Um, but anyways, as I was saying, we this is what we got. This is what we got from the left side. This is what we got from a plus b times a minus b, and this is what we got from a squared minus b squared. No, I got it backwards. Hold on. Yeah, right? Yeah. This is from the left side. I mean, this is from the right side. This is from the left side. Flipped it up. Anyway, so the only way in which these two can be equal is if the original matrices are diagonal. Is let's say A and what was it? A and D are real numbers, R, S, and the other wasn't zero. And then B is like T, B, 0, 0. It's like you're gonna get to this, and you're gonna get to this, and so what you're gonna get is the same. If it's a diagonal matrix, it's gonna behave much like a number, like a usual number, right? So yeah, that's how you show it, I think. Got lost in thought. If there is no sound to this, I am gonna go cry in a corner. It's it's too much. It's just too much. Um, so you got a plus b, expand a plus b cubed. All right, I'm gonna take it that a and b are diagonal to make this a lot easier. So let's say A is R has 0, 0, right? B is T V 0, 0, where R is T V are in real numbers. Dang it. There we go. Are in real numbers. And so A plus B equals R plus T. Dang it. R plus T 0, 0, S plus V, right? And this times itself is, dang it, R plus T, dang it, R plus T, 0, 0, S plus V, right? So they're gonna behave like numbers because, like this multiplied by this, only these two are gonna be multiplied, and then only these two are gonna be multiplied, right? So it's just like multiplying numbers. It's gonna be R plus T squared, R plus T squared, 0, 0, S plus V squared. It's basically just gonna be the same numbers all throughout. 0, S plus V, right? Cubed. Right? I can do a little more expansion if you do R plus T times R plus T, and then plus 0 times 0. That is the first multiplication. The second multiplication is going to be 0 times 0, 0 plus 0, right? Because this multiplies to that, and this multiplies to that. Next is going to be also 0 plus 0, because, again, this multiplies to that, the 0, and this multiplies to the 0 here. And then it's going to be S plus V squared, or S plus V times S plus V. Because the 0 multiplies to each other, and the non-zeros multiply to each other. So that's why we get R plus T squared and S plus V squared, and that's how we get to that. Like it says expand A plus B cubed, and I assume that it says like the A plus B, like the A and B that make it possible to, or like the A and B where the difference of squares, in which the difference of squares can be applied. So I'm gonna leave it at that because I don't want to do much more computations. I want to get past this problem, honestly. Technical difficulties are very harsh. Wow. So next question. Let D be the diagonal matrix. All right, so we got D1, 2, Dn. And by extension, we have 0, 0. Oh, sorry. 0, 0, 0, 0, 0. All right. So that's where we have it. That's our matrix. That's our matrix. And let Ij be any n by n matrix. All right. We're gonna have the same for A. That matrix A. Wait, 1, 1, 2, 2. Oh wait. Meet the products of dA and AD. right? Right? Aij, not II. So it probably means like it means A12, A21, A22, A1n, A2n, A n1, A n2, A n n probably means that. So like that's A, this is D, and this is A. Computer products DA and AD. It is going to be the same. It is going to be the same because it's a, like I said before, uh, a diagonal matrix is it is just gonna behave like a number. And so if you multiply a matrix by a diagonal matrix, um, you're just gonna be left with the elements of the diagonal. There's like this times this, for example, it's gonna be d1 plus 0 plus 0 plus 0 plus da 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 da. Because oh my god, like I was saying, it's gonna be sorry, we had another technical difficulty. I need to get my shit together. Oh my god. Anyway, um, I this is not being a good run through. Ah, who knows? Anyway, uh, yeah, it's basically gonna be you're gonna be um multiplying everything else by 0. So you're just gonna be left with D1 A11, right? And for the second one, you're gonna have 0 for the second, like this and this. Um, no, wait. Actually, no. Hold on. Hold on. All right. That's for the first one, right? Next, you're gonna have 0 plus D1 A12 plus 0 plus 0 plus 0, da, da, da. And then so on and so forth. Oh, oh, I see. I see. I see. So it's just, yeah. Yeah, so it's just gonna be, um, we can generalize it. It's like for this, no, hold on. For this, it's gonna be 0 plus D2 A21 plus 0 plus 0 plus 0. And then for the second one, it's gonna be 0. Uh, Let me erase this. That's not true. I don't know what's happening. I don't know what's happening today. I'm not in my best shape technically and literally. So yeah. Next we're gonna have 0 plus D2 A22 plus 0 plus 0 plus 0. Da 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 da. Right. Then for the third one, let's go straight to the end. Since it's all zeros except for the end, it's going to be 0 plus 0 plus 0, da 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 da, plus dn a and 1, right? And then 0 plus 0 plus 0, da 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 da, da plus dn a and 2, right? So this is equal to, we can put it together, d1 a11. Let me put it in 2 boxes. D1, A1, 1, right? That, D1, A1. D1, A1, N, D2, A2, N, that, DN, AN, N, that, that, D2, A21, D2, A22, that, DN, AN1, DN, AN2, and that is our product. That's how you multiply a matrix times a diagonal matrix. Yay! Finished this video. It's been 52 minutes and we've gone through only uh hold on. 1, 2, 3, 4, 3 and a third questions. It has been a rough video, not gonna lie. I've had so many difficulties. But anyway, that's fuck it. That's it. All right. That's the video. What we've done today is um we found a formula for an upper triangular matrix of all ones raised to the nth power, proven it by induction, not formally, but you know I've shown it. We've done matrix block multiplication. We've proven that, or we've shown that the difference of squares can be applied to matrices only if they're both diagonal, and we've shown how the general formula of multiplication between a diagonal matrix and a non-diagonal matrix functions or works or goes about, right? And so yeah, that's all that we've done today. If you like the video, like it. If you want to see more videos like this, subscribe. Um, so yeah, it has been a pleasure. Not really. Um, see you in the next video. Bye bye.